depression in freezing point of solvent. Delta TF. So freezing point is exactly opposite process for the evaporation. So earlier we discussed the evaporation. Now let us discuss how the freezing process occurs. During the freezing process, we must understand one thing, that when a liquid is taken, liquid molecules usually arrange little bit away from each other when compared to the solid molecules. So during freezing, we have to bring this, because we have to convert the liquid into the solid state. To convert the liquid into the solid state, the molecules must and should come close to each other. To bring the molecules close to each other, we need to do two things. One is increasing pressure, second one is reducing the temperature. But liquids are incompressible to the pressure. Pressure effect is negligible. That's why we cannot apply the pressure on the liquids to convert them into the solids. So we have only one option, that is by reducing the temperature. So when temperature removes, then automatically the movement of the molecules decreases, so that they settles down and they get the sufficient time to develop the attraction forces. So when they come close to each other, when sufficient amount of strong attractive forces are developed, it becomes the solid. And attraction forces, developing of attraction forces is an exothermic process. So that this energy has to be removed. That is what we are doing by decreasing the temperature. So freezing occurs during the cooling process. Cooling process in the sense removing the temperature. Now, if you add some amount of the solute to this solvent molecules, then these solute molecules distribute in between the solvent molecules, so that solvent molecules do not get sufficient process or sufficient way to come close to each other and to develop the attractive forces, because these solute molecules interrupt the freezing of the solvent molecules. Remember, during the freezing, only solvent freezes out, but not the solute molecules. So when solute molecules are interrupting the solvent attraction forces, then we need to reduce the temperature still lower, so that these reducing temperature will force the molecules to come as much as possible close to each other, bypassing the solute molecules, so that they develop the attraction forces and become the solid. That means here, compared to the solvent, for solution we are reducing the even lower temperatures. We are decreasing so much of temperature. That means the solution boiling point, freezing point is less than the solvent freezing point. If more amount of solute you added, then the solution becomes more concentrated, more solute molecules interrupt the solvent molecules, so that we need to create the even lower temperatures to make the solvent as a solid. That means when the concentration of solution increases, freezing point also gradually decreases. This is the general phenomenon what we discuss it. So let us define the freezing point also. As we discussed in the earlier case, boiling point of the solution solvent was defined as the temperature at which the vapor pressure is equals to atmospheric pressure is called the boiling point. Now freezing point also let us try to define using the same vapor pressure. Now let's take the condition. We know that freezing process is nothing but the liquid is converting into the solid. But exactly at a freezing point, we can say that both liquid and solid are in equilibrium. Liquid exists as well as solid exists. Example, if you get confused here, exactly at 0 degree centigrade and without changing any temperature or heat energy, in an isolated isothermal condition or adiabatic system if you take, so insulated container, if you keep some 1 kg of the water and 1 kg of the ice in the insulated container at exactly 0 degree centigrade, even after some time or after 1 hour or 2 hours also, you cannot find that ice melts and the water freezes out. Why? Because the mass of the ice, the mass of the water remains same, but ice starts melting at the same time water also starts freezing, because at the same temperature ice melts as well as the water freezes out. So both dynamic process takes place but with equal rate. That means at a freezing point, both liquid and solid are in equilibrium. So whatever the temperature it may be, every time liquid always vaporizes so that it has some amount of the pressure. That is what called as its vapor pressure. I am taking the pure solvent, so that representing P naught. And whatever the vapor pressure the solvent is having, the same vapor pressure we can apply to the solid solvent. So the question is, how the solid solvent is having the vapor pressure? Solid directly is not having the vapor pressure, but it is in the equilibrium with the liquid. If more pressure we apply here, even though these are incompressible to the pressure, whatever the pressure the liquid is having, the same pressure we can apply to the solid also, because both are in equilibrium. So now the question is, both the vapor pressure of the liquid as well as the vapor pressure of the same liquid in the solid state are same at equilibrium. So freezing point can be defined as the temperature at which the vapor pressure of a liquid is equals to the vapor pressure of the solid solvent. That is what called the freezing point. So I shall write down the definition. The temperature at which the vapor pressure of a liquid is equal to the vapor pressure of solid solvent is called its freezing point. So at freezing point, anyhow, since they are in equilibrium with each other, their vapor pressure is also same. The same vapor pressure we can apply to the solid as well. So let us see this one in the graphical representation. So in the graphical representation, if we take a graph, that is vapor pressure versus temperature in kelvins. So the solvent, as we said here, liquid vapor pressure must be equals to the vapor pressure in the solid state at equilibrium, so that whenever you are reducing the temperature, the solvent freezes at a particular point. So this could be the freezing point of the solvent. Let us take it as a T0 TF solvent. And if you take the solution, so in the case of the solution, as amount of solute is present, so that vapor pressure of the both solvent decrease, so that solution also decrease. Then automatically it needs even lower temperatures to match that vapor pressure is equals to the solid liquid vapor pressure, so that whenever solution is freezed, whenever decrease the temperature, so it freezes even at the lower temperatures of the solvent. So it freezes at a particular point TF. Let us take it as a 1, solution 1, having some concentration. Even if you take the higher concentration, then it comes like this. This is TF2. This is the solution 2. So what are the important things we can observe from this is, these are the points. I am taking the point A, point B and point C. Remember that at these particular points, the vapor pressure of the liquid solvent is equal to the vapor pressure of the solid solvent. So for solvent, the vapor pressure of the liquid solvent is equal to the solid solvent at point A, and for solution 1 it is at point B, and for solution 2 it is at point C. So solution 1 to solution 2 concentration increases and freezing point value gradually decreases. And here difference in the freezing point, how to calculate means higher value minus lower value. Which is the higher value here? T0F. That means here the freezing point of the solvent is always higher than the freezing point of the solution, and difference of the freezing points, that is what called the depression in freezing point. Why? Because the freezing point is decreased. So that decrease in freezing point is called the depression in freezing point, which can be calculated by higher value subtracting the lower value from the higher value. Here higher value is T0F, lower value is TF. And if you observe here, from here to here and from here to here, when the concentration of the solution increase, the gap widens. That means freezing point difference gradually increase. So we can say that delta TF is directly proportional to the concentration. That concentration we are taking in terms of the molality. We discussed already in the elevation of boiling point what is the necessary for the to take the molality, because it is independent of the temperature, which will not change basically the concentration of the solution taken. Now let us try to replace this proportional symbol using a constant. So delta TF equals to some constant Kf into M, where M stands for the molality. Even if you elaborate it, so that we get the delta TF equals to Kf into weight of solute by molecular weight of solute into 1000 by weight of the solvent in grams. So this is the formula. Now let us discuss about the Kf. So what is Kf? Kf is known as molar depression constant, or freezing point depression constant, or it is also known as the cryoscopic constant. Then how to calculate the Kf value? Kf value can be calculated by using the formula Kf equals to R T naught F square divided by 1000 into LF, where LF means latent heat of fusion. And how to calculate the latent heat of fusion means, so latent heat of fusion equals to enthalpy of fusion divided by molecular weight of solvent. So let us substitute this value there. So we get Kf value equals to R T naught F square divided by 1000 into molecular weight of solvent divided by delta H of fusion. So again here R value, universal gas constant, is a constant. Freezing point of the solvent is always constant, and 1000 constant. Enthalpy of fusion particular solvent is constant. So that Kf value again depends on the molecular mass of the solvent. That means nature of the solvent. When solvent changes, automatically Kf value also changes. So we can write down that it depends on the solvent. Then what are the units? Units are kelvins, kg per mole, or else kelvins per molality. So how to get kelvins per molality means you send the molality this side, temperature units are kelvins, difference of temperature divided by molality. So this is about the freezing point. Now the question is, what are the necessary conditions for the elevation boiling point of a solution and depression freezing point of the solvent, in both case solvent? And in case of elevation of boiling point of the solvent, the solute must be non-volatile. If a solute is non-volatile, then only we can observe the elevation boiling point of the solvent. What happens if solute is volatile? So that question again leads to the non-ideal solutions, where they may show the higher boiling point or the lower boiling point. So that conditions changes. So it may increase the boiling point, it may decrease. But if the non-volatile solute is added, then obviously we can get the elevation in the boiling point. So for elevation in the boiling point, the solute must be non-volatile. Then what about the depression freezing point? In case of the depression freezing point, the solute, whatever we are adding the solute here, the solute not necessary to be in the non-volatile solute. You can take the even volatile solute also. For example, if you add the NaCl, the freezing point of the solution solvent decreases, as well as 35% volume by volume ethylene glycol also acts as antifreeze, means which decreases the freezing point of the water to the minus 17 degrees centigrade approximately. That means here for the depression freezing point, the solute not necessary to be a non-volatile one. It can be a volatile one or non-volatile, but for elevation of boiling point, it must be non-volatile solute. Now let us see the relation between the delta TF and delta TB, elevation boiling point and depression freezing point. We know that elevation boiling point delta TB equals to Kb into M, equation 1, and delta TF equals to Kf into M, equation 2. Now divide equation 1 by equation 2 so that we get the delta TB by delta TF equals to Kb into molality by Kf into molality. See that if molalities are different, then this formula is applicable. If molalities are same for same concentration, then concentration cancel out so that we get the delta TB by delta TF equals to Kb by Kf. So by using this and by knowing the freezing point, we can calculate the boiling point. If by knowing the boiling point, we can calculate the freezing point of the solution.